to the fourth lesson of module 5, which is on bending of beams, part 4. Well, in the last lesson we have looked into the aspects of shear force and bending moment, and we have introduced how to draw the shear force and bending moment diagrams. Now, in this particular lesson we are going to look into some more aspects of shear force and bending moment diagram, and it is expected that once this particular lesson is completed, one should be able to understand the different characteristics of shear force and bending moment diagrams. Now, in the last lesson we have introduced how to draw shear force and bending moment diagram for different kinds of beams subjected to different kinds of loads. Now, we will analyze those beams for which we have drawn the shear force and the bending moment diagram, and we will look into that the different salient features of shear force and bending moment diagram, and then we will be looking into some more examples of different kinds of beams which are subjected to different kinds of loading, and how to plot the shear force and bending moment diagram for those beams. Now, one should be in a position to evaluate the reactive forces, the shear force and bending moment for different beams and for different types of loading, and also one should be able to draw shear force and bending moment diagrams for such beams. And hence, the scope of this particular lesson includes the recapitulation of previous lesson. We will be looking into the aspects which we have discussed about the shear force and bending moment diagram. The different features of shear force and bending moment diagrams, we will be looking into it in a more elaborate way. Also, we will be looking into some examples for evaluation of reactive forces, shear force and bending moment for different beams under different loading conditions, and we will plot the shear force diagram and the bending moment diagram for those beams. Now, to recapitulate the aspects which we have discussed in the previous lesson, let us look into the answers of the questions which were posed in the last lesson. Now, the first question which was posed was what is the value of shear force where tangent to the bending moment diagram is horizontal. Now, let us look into this aspect of it. In the last lesson we had seen that the differential equation dV dx in the along the length of the beam is equals to Q, where V is the shear force and Q is the loading, uniformly distributed load. Now, this aspect we have looked into, that if we have Q equals to 0, then what happens to V. Now, subsequently we had looked into that if we take the differential of this moment dm dx, this is equals to minus V. Now, if the shear force V is equals to 0, then we had said that dm dx equals to 0, and over that particular zone moment shows as a constant. Now, the question posed here is that in the other way, that if the dm dx is 0, that means if we have this particular problem we had solved last time, wherein a simply supported beam, one end is on a hinge support, other end is on a roller support, and if this beam is subjected to uniformly distributed load, then what will be the shear force and the bending moment diagram. And we had looked into how to plot the shear force and the bending moment diagram, and the diagram, shear force diagram and the bending moment diagrams are as shown over here. This is the shear force diagram and this is the bending moment diagram. Now, as you can observe from this bending moment diagram, that at this particular point the tangent to the bending moment diagram is horizontal one. So, it indicates that the derivative at that point dm dx is equals to 0. Now, from this, corresponding to this, as we can see, the shear force at this particular point is equals to 0. Now, let us look into another problem to describe that what happens if the tangent is horizontal at a point in a bending moment diagram. Now, let us look into this particular example where again the beam is a simply supported one, having a hinge support here and a roller support over here, and it is subjected to a concentrated load. Let us say this concentrated load is 100 kilonewton. Now, if we try to draw the shear force and the bending moment diagram of this particular beam, then as there is no horizontal force in this, so we will have the value of HA as equals to 0 from summation of horizontal force 0. Here we have the vertical reactive force RA, and for the roller support we have the vertical reactive force RB. So, summation of horizontal force equals to 0 will lead us that HA is equals to 0. Now, RA and RB are the two vertical reactions, and since the beam is symmetrical and we have a load of 100 kilonewton which is concentrated at the center, it is at the center of the beam at a distance of 5 meter from here, and we have 8 kilonewton per meter uniformly distributed load over the entire span. So, the reactive values RA and RB, if we write down RA plus RB equals to the vertical force 100 plus 80 times 10, and then if we take the moment of all the forces with respect to A, we can evaluate the value of RB, and therefore, you will find that RA and RB will be equals to 90 kilonewton, is a half of the total load that is being carried by the beam, because RA and RB, they are symmetrically supporting the whole beam and the load is also symmetrical. So, the reactive values of RA and RB, they are same, and the magnitude is equals to 90 kilonewton. Now, if we take the free body diagram of this particular, supposing we cut the beam at this location, let us say this is AA, and take the free body of this particular part, then we have the reactive force RA over here, we have the distributed load which is at 8 kilonewton per meter, we have the shear force V and the bending moment M at this cut section. So, if we take the vertical equilibrium, the equilibrium of the vertical forces, then V plus RA, they are in the same direction, minus 8 kilonewton per meter, and this section is at a distance of x. So, minus 8 times x equals to 0. So, this gives us a value of 8x minus 90, and this particular expression, that means it is valid, the load is constant from A up to the point where the concentrated load acts. So, just before the concentrated load, everywhere the loading situation is the same. So, the shear force will be guided by this particular expression. So, at x equals to 0, we get a value of shear force which is equals to minus 90, and this is what is reflected over here, that as x equal to 0, the ordinate is minus 90. Now, at x equals to 5, that means just before this concentrated load, if we try to calculate the value of the shear force for x equals to 5, V is equals to 5 times 80, which is 40, minus 90. So, this is equals to minus 50. So, the value at this particular point is equals to minus 50. Now, if I at this particular point, if I exaggerate the shear force diagram, now precisely the concentrated load acts at this particular point. Now, we are evaluating the value of the shear force a little left to this load. So, basically we have the ordinate over here as 50. Likewise, if we take, so let us assume for the time being that we have this variation from here to here, which is linearly varying with respect to x. Now, if we like to find out the value of the shear force immediately after this 100 kilonewton load, let us take a section here at this point, which is again at a distance of x, variable distance x, wherein we include this concentrated load as well. And if we draw the free body diagram of this particular portion, then we have the reactive force RA, we have the concentrated load which is at a distance of 5 meter, and we have uniformly distributed load over the entire length of x, and as usual we will have a reactive force V and the bending moment M. So, this is V and M. Now, if we compute the value of shear force V, and if we take the equilibrium of the vertical forces, then V is equals to, because V plus RA minus 100 kilonewton minus 8 times x, this is equals to 0. So, this gives us minus V equals to minus RA plus 100 plus 8x. Now, here if we substitute the value of x just next to this load point, which is approximately equals to 5, then this becomes 8 times 5, 40. So, this is 140, and RA is equals to 90. So, this becomes equals to 50 and this is plus 50. On this side we had minus 50 and on this side of the loading we have plus 50. So, here we get the ordinate over here. So, basically if we enlarge this particular part, it will appear that we have a variation like this, but this distance being very small, we take this as a straight line. So, there is a jump of the shear force from minus 50 to the plus 50 immediately after this load point. And then if we compute the value of shear force at this end, where x is equals to 10 meter, in this particular expression if we substitute the value of x as 10 meter, then 8 times x is 10, 80, so 180 minus 90, so this gives us a value of 90, which is the shear force at this end. So, it goes again linearly varies and comes down to this place. So, this is the variation of the shear force for this particular beam, where it is subjected to uniformly distributed load of intensity 8 kilonewton per meter and has a concentrated load at the center of the beam, which is equals to 100 kilonewton. Now, if you look into the values of the bending moment correspondingly, in the first case when we had taken this particular free body, here we had the bending moment as m, and if we take the moment of all the forces with respect to this particular section, then we have m as equals to r into x minus 8 into x square by 2, and this gives us, once we substitute the value of Ra as equals to 90 times x minus 4 times x square. So, if we substitute again the value of x as equals to 0, then the value of the bending moment becomes 0, which is reflected here. Now, at x equals to 5, just on the left side of the load, if we substitute the value of x as 5, so this becomes 450 minus this is 100, so this is 350. So, 350 kilonewton meter is the load on the left side of this particular concentrated load. Now, if we take the other free body diagram, which is a section beyond the load point, and take the free body of this left part, and if we compute the value of the bending moment there, we have bending moment as equals to Ra into x, here this reactive force is Ra, minus 8 into x square by 2 minus 100 into x minus 5, this is at a distance of 5 meter. So, this is the expression for the bending moment. Now, here if we substitute the value of x equals to 5 again, which is just after the concentrated load point, then this term becomes 0, Ra is equals to 90. So, 90 times 5 is 450 minus x is again 5. So, this is 100, this is again equals to 350. So, if you look into that, from both the expressions we get the value of bending moment at this point as 350. And if you remember that when we were trying to establish the relationship between the loading and the shear force and the bending moment, we had seen that when we have considered a small segment of the beam in which a concentrated load acts, the changeover from the left end of the load to the right end of the load, there is little variation of the bending moment, which is negligibly small, and thereby the moment at that particular point, because of the concentrated load, does not change at all. So, this is the magnitude of the 350 kilonewton meter, and if you compute the bending moment with this expression again, when x is equals to 10 meter, you will find that m is equals to 0. This is 10 minus 5 is 5, this is 500, and this is 10 square means 400, and this is 900. So, this gives us 0. So, this is the, and this is a parabolic distribution. So, this is the bending moment diagram for this particular loading. Now, at this point, this is the maximum bending moment, which is 350 kilonewton per meter, and this is the point, as we have seen, that where we have a concentrated load, though there is no change in the bending moment, but the rate of change of the bending moment from the left of the concentrated load to the right of the concentrated load changes immediately, and this is what is happening here. Now, if you look into that, there is a positive slope, whereas from here the slope is a negative slope. Now, at this particular point, if we take the tangent to this bending moment diagram, this tangent is a horizontal one, and thereby the dm dx is 0 for this particular case. Now, correspondingly, if you look into the value of the shear force here, now in this case the shear force changes its sign at the point of the concentrated load from negative to the positive value. So, in fact, in the bending moment diagram, at a particular point, if the tangent drawn is a horizontal one, then as we have seen right now from these two problems, that either we get the value of the shear force as 0 or the shear force changes its sign from the negative to the positive or the vice versa. So, this is what it happens. Now, if you again go back to that expression that dm dx is equals to minus v, if shear force is equals to 0, then we can readily say dm dx equals to 0 or moment is constant, or if dm dx is 0, then either v is 0 or v changes its sign from the negative to the positive or positive to the negative. So, this is the consequence of the particular question. Now, the answer to that question then is the point at which the tangent to the bending moment diagram is horizontal, there the shear force at that point is either 0 or changes its sign. Now, let us look into the second question, that what is the value of bending moment in a hinged and a roller support. Now, this question of course is quite straightforward, and as we have seen when we are evaluating the reactive forces at the hinge support and the roller support, also when we have discussed the different kinds of supports, we have seen that in case of a hinge support, it is constrained to move against the horizontal and the vertical direction, but it is allowed to rotate. So, thereby there is no restraint on the rotation, and thereby it cannot sustain any moment. And so is at the roller support. At the roller support we had seen that it is allowed to move in the horizontal direction because of those rollers, and thereby it cannot have any restraint in the horizontal direction, but in the vertical direction we are putting restraint, that means it is not allowed to move, and thereby there will be reactive forces in the vertical direction. Whereas it is at the roller support, again the beam is allowed to rotate, that means there is no restraint on the rotation or it cannot resist any bending moment. So, the values of the bending moment both at the hinge support and as well as at the roller support, they are 0. So, this is what is stated over here, that the value of bending moment at the hinge or at the roller support is 0, as these supports are not constrained against rotation. Now, let us look into the last question, which is what is the effect of concentrated moment at a point in a beam on shear force at that particular point. Now, we have looked into what are the effects of the distributed load in the beam, what are the effect of concentrated load at a point, how it affects the shear force and the bending moment on either side. Now, in a beam at a particular point, if there is a concentrated moment, then how does that affect the shear force at that particular point. Now, to answer that question, let us look into this particular diagram once again, that a segment of the beam of length dx is subjected to a concentrated moment m0, and these are the values of the shear force and bending moment on either side of the section. Now, if we take the equilibrium of the vertical forces, then we have this particular expression, that V plus V1 which is acting upward minus V which is acting downward, this is equals to 0. So, thereby this gives us V1 equals to 0. That means, in a beam at a point where there is a concentrated moment, then it does not affect the shear force. So, there will not be any change in the shear force level when you plot the shear force diagram. Wherever you have the concentrated moment, it does not affect the shear force diagram. So, there will not be any change in the shear force value. Well, now that in the last lesson we had discussed about the features of shear force and bending moment diagram, how to plot shear force and bending moment diagram, and we had defined what is shear force and bending moment diagram. Now, based on the examples which we had seen last time, both for the concentrated load, a simply supported beam subjected to a concentrated load, or a simply supported beam subjected to uniformly distributed load, let us look into some of the salient features of shear force and bending moment diagram. Now, if you notice this, that the shear force and the bending moment diagram which we had plotted for a beam which is a AB subjected to a concentrated load P at a distance of A, and this of course is on a hinge support and this on a roller support, and since there are no horizontal force, we said H is equals to 0, and we have these two vertical supports, and correspondingly we have this as our shear force diagram. This we call as shear force diagram, and this is our bending moment diagram. Now, from these, if you look into the slope dV dx, that means the rate of change of shear along the length for this part as well as this part, which is x is between 0 to a or x is between a to L, we find that there is shear force diagram, the dV dx value of shear force diagram is 0. So, which is the case, because dV dx as we know is equals to q, and if q is equals to 0, expectedly dV dx is equals to 0, and this is what is happening over here in this particular diagram. Now, here as you have seen that dm dx is equals to minus b, this is the expression which we have derived. Now, if you look into this expression over here, now at this particular point, this is the bending moment diagram, here we have the magnitude which is equals to PAB by L, and at this point the bending moment value is equals to 0. So, the dm dx, the slope over here, is equals to this moment minus this moment divided by this length L. So, PAB by L minus 0 by A gives us PB by L, and negative of PB by L is the shear force at this particular location. So, this equation again matches diagrammatically over here, and so is on this particular part. Now, here if you look into the slope, here PAB by L and this is 0. So, the slope here, the dm dx at this particular zone is equals to 0 minus PAB by L divided by B, which is equals to minus PB by L, and minus PB by L minus of that is equals to PB by L. I am sorry, B, if you divide by B, this is PA by L, so this is equals to PA by L. So, this is the value of the dm dx or the slope, which you can readily see from the shear force and bending moment diagram. Also, now we have seen that if we take the derivative of this, if we like to find out the difference between the bending moment at two different sections, if we integrate the dm between A and B, which gives us the moment value at B minus moment value at A, that is equals to integral V dx. Now, from this particular expression we can find out the between these two, that integral of dm is equals to V times dx. So, if we calculate the bending moment values at these 2 points mb minus ma, this is equals to integral V dx. Now, if we choose these 2 points B and A, then the difference in the bending moment values between these two ends is 0, because the bending moment here is 0 and bending moment here is equals to 0. So, mb minus ma value, this is equals to 0 between these 2 points. Now, let us look into that if we take the shear force diagram between these 2 points, now here this is Pb by L, which is negative, multiplied by A. So, this is minus Pab by L, and over this region we have Pa by L multiplied by B, which is plus. So, we have Pab by L plus. So, if we sum them up, this gives us 0. So, again this satisfies that area of shear force diagram between A and B is equals to 0. So, these are the observations from this particular diagram. Now, let us look into some more aspects on this. Now, the maximum positive and negative bending moments in a beam may occur in the following cases. Number 1, a cross section where a concentrated load is applied and the shear force changes sign. Now, this aspect we have seen that right now we have solved one example wherein on a uniformly distributed on a beam where uniformly distributed load is there, we have a concentrated load as well, and we have seen in the shear force diagram the sign changes from the negative to the positive. So, wherever we have a concentrated load, there the shear force changes its sign. Also, it is expected that the maximum bending, and there we have seen that the maximum bending moment occurs at that particular point. Also, maximum bending moment occurs at a point or a section where the shear force is 0. Wherever the shear force is 0, we expect that the bending moment there is the maximum. Now, a point of support where vertical reaction is present, there also, now this we will look into through an example, that if you have a beam wherein it is simply supported or hinged on one end and supported on roller on the other, and you have overhang, and therefore, at the roller support you have a vertical reaction. Now, in this particular point you may get a vertical, a negative moment, a moment at the support point which could be maximum. So, this is what is mentioned, that maximum bending moment may occur at a support point where you have vertical reaction, and a cross section where a couple or a moment is present. So, these are the situations where you can expect the value of the bending moment could be maximum at those points. This could be positive maximum or a negative maximum. That means, we talk about the magnitude of that bending moment, it could be on the negative side as well as could be the positive side. Okay. Now, we having known these aspects of the bending moment and shear force diagram, now we are in a position to summarize that what are the steps necessary for drawing the shear force and the bending moment diagram. Now, given a beam to you with certain kinds of loading and with certain kinds of support conditions, and of course, the reactive values of the support should be such which can be evaluated using the equations of statics. That means, they are statically determinate system. Now, if you have such a system and if we are interested to draw the shear force and the bending moment diagram, then how do you go about it? What are the different steps? The first thing, as you have noticed, is that we draw the free body diagram of the whole beam, and thereby we represent the supports with the reactive forces, and we try to evaluate those reactive forces based on the equations of equilibrium. So, the first step will be the evaluate the reactive forces considering the free body of the whole beam. Then you will have to divide the beam into segments in which load is continuous. Now, as we have noted, supposing if we have a beam which is uniformly distributed, subjected to uniformly distributed load with say several concentrated loads. Now, if we look into this particular segment from here up to the load point, they have uniform kind of a loading. Now, from this point to this point, we can see that uniform load with one concentrated load. From this point to this point, we see this is uniformly distributed load with two concentrated load. From this point to this point, we have uniformly distributed load with three concentrated load from this left edge. So, if we divide into this number of segments, if we divide the whole of the beam into these individual segments, and then corresponding to those segments, if we try to draw a free body diagram taking a cut in the beam, and at the cut, as we have seen, that we will have the resultant shear result, stress resultants, which are shearing force and the bending moment, and those values of shear force and the bending moment for that particular segment can be evaluated depending on the loads and the reactive forces we have. So, corresponding to each of these segments, if we evaluate the values of the shear force and the bending moment, and if we plot the ordinates of those along the length of the beam, the diagram which we will get will give us the diagram for the shear force or the bending moment, as the case may be. So, this is what is mentioned over here, that evaluate the shear force and bending moment on the free body of each segment, and plot the variation of shear force and bending moment for each of such segments. So, once you do that, then you will get the shear force diagram and the free body and the bending moment diagram of that particular beam. So, these are the steps through which one has to go through to draw the shear force of the bending moment diagram. Well, now let us look into some more examples on how to evaluate the reactive forces and draw the shear force and bending moment diagram. Now, here we will have to draw the shear force and bending moment diagram for the beam in which the two concentrated loads P are placed, which are symmetrically with respect to the beam, and which is at a distance of A from the left support, and this is at a distance of A from the right support, and the length of the beam is L. Now, all we need to do is that to evaluate the or to draw the shear force and the bending moment diagram. Now, as we have done in the past, what we need to do is we replace these supports, that means we draw the free body diagram of the whole beam. So, here we have a vertical reaction and a horizontal reaction, and at the roller support we will have a vertical reaction, and we call this as R A and this as R B for the beam A B, and the horizontal force H is H A. Now, as we have seen or in this particular beam that summation of horizontal force equals to 0 gives us the value of HA as equals to 0. Now, summation of vertical force is 0, RA plus RB is equals to, we have 2 P values. So, this is equals to twice P. Now, if we take the moment of all the forces with respect to let us say A, then we have RB into L, which is anti-clockwise, and both the loads cause a clockwise moment with respect to this particular point. So, this is equals to P times A for this load plus P times L minus A for this load. So, P times A minus P times A gets cancelled. So, this is equals to P times L. So, this gives us the value of RB is equals to P, and since RA plus RB equals to 2P, so RA also is equals to P. So, the reactive values RA and RB is equals to P. Now, the whole of the beam can be divided into 3 segments. This is segment 1 from A to, let us call this point as C, from here to here is another point which is D, and this is B. So, we have clearly 3 segments, segment 1, segment 2 and segment 3. Now, in the first segment, if we take a section and draw the free body diagram, we have the left part wherein we have the reactive force RA, which is equals to P, horizontal force is 0, and on this we do not have any other load, and at this cut we have a shear force V and a bending moment M. So, if we have that, then at any section we find, and if we take the vertical equilibrium, that V is plus P equals to 0. So, this gives us the value of V as equals to minus P. So, in the segment 1 from the point A up to this particular point, everywhere the shear force is equals to minus P. Now, if we take the segment over here, then what happens to this particular diagram, let us see. Now, as we have seen that on the left segments, on the segment 1 after taking the free body, we have V is equals to minus P. Now, let us take a segment here, or in this segment we cut a free body diagram, and the free body diagram looks like this. Here we have the reactive force RA, which is equals to P. We have the value of force P, which is at a distance of A, and at this point we have the shear force and the bending moment as B and M. Now, if we take the equilibrium of the vertical forces here, it gives us that V plus the reactive force P minus the load P is equals to 0. So, this gives us V as equals to 0. So, from here to here in the segment 2, wherever you take a section, you get identical free body, and hence from this point to this point the shear force is equals to 0. Now, if we take the segment 3 and cut it here and take the free body of the left part, then this is the free body diagram. We have the reactive force P here, we have the loading applied P, which is at a distance of A, we have another loading applied which is at a distance of, total length is L, this is A, this is A, so this is L minus twice A. Now, here again you have the shear force B and the bending moment M. Now, if we take the equilibrium of the vertical forces here, we have V plus P, the reactive force here, then the loading P and P, which is minus twice P, this is equals to 0. So, this gives us a value of B as equals to P. So, between this loading point to the end, wherever we take a section, we get the identical free body diagram, and hence V is equals to P over the entire region. So, as you can see over here that on this segment 1 we have a shear force which is negative and constant in this particular region. Between this point and this point the shear force is equals to 0, and from this loading point up to the end again we have a shear force which is uniform and having a magnitude equals to P. So, this is what is the shear force diagram for this particular beam. Now, if we try to find out the bending moment values, let us look into the values of the bending moment. Now, for this particular segment where the reactive force is P, we have B and M, and this M is equals to P times x, this distance being x, and M is anticlockwise, this P is causing a clockwise moment. So, P times x is the moment. So, at when x is equals to 0, the moment is equals to 0, and this is the value which is shown over here. Now, at a distance of a, just before this load point, the value of bending moment is equals to P times a. So, this is the magnitude of the bending moment over here. Now, corresponding to this particular section in this segment, if we take a section here, this is the free body diagram, and here we have the bending moment M. Now, if we take the moment of all the forces with respect to this particular point, we have M, which is anticlockwise, then this reactive force cause a clockwise moment. So, minus P times x, and this load causes anticlockwise moment. So, this is plus P times x minus a, this is equals to 0. So, this gives us a value of M as equals to P into x minus P into x minus a. Now, if we substitute the value of x as equals to a, which is just after this load, then we find that again contribution of this equals to 0. So, M is equals to P times a. So, wherever we take section between these 2 points, we have the value of bending moment equals to P into a, and which is reflected over here in this diagram. As you can see that from here to here, the bending moment is constant. Now, corresponding to this particular segment, when we take a section over here, we have the shear force as V and the bending moment at this section as M. And if we write down the moment equation here, the moment equation comes as M, which is again in the anticlockwise direction, minus P times, this is the value of P, so P into x, P times x. Then we have these 2 loads, one, this distance being x, this is a. So, this cause a moment which is again in the clockwise anticlockwise direction, which is positive. So, this is P into x minus a plus P into this x minus this distance, which is equals to L minus a. I mean this distance is x. So, x minus a minus L minus 2a. So, this is plus, so L plus a. So, this gives us, so we can write this as equals to P into, let us explain the whole thing in general. So, the value of this is equals to plus P into x minus a minus L minus 2a. So, this is equals to 0. So, the whole thing comes then as equals to M is equals to P into x minus P into x minus a and minus P into x minus a minus L plus a. So, this is x minus L plus a. So, this is the value of the bending moment. Now, here if we substitute the values, that means at this particular point, if you said that x is equals to L, then you see this is L minus a and this is L minus s of a, P times L, this is equals to 0. So, at this point again at x equals to L, we find that the bending moment equals to 0. So, and also if we substitute x as L minus a, we get the value of bending moment as equals to P times a, which is at this point. So, as you can see now from this free bodies of the different segments, we get a bending moment which is varying like this. Now, if you remember that we had looked into that wherever the shear force is equals to 0, their bending moment is expected to be constant, that because dm dx is equals to minus v. So, if shear force v is equals to 0, then moment at that particular point or that portion of the beam is expected to be constant, and that is what is reflected over here. Now, in this particular zone, as we can see, the value of the shear force is equals to 0, and hence the value of the bending moment in this particular zone is constant, and here it is linearly varying from 0 to P to A and from P to A to 0. And again, if you take the slope, here you see that P times A minus 0 by A is P, and negative of P is the shear force here, and again here 0 minus Pa by A, so minus P, so minus P minus or minus P equals to plus P, which is the shear at this particular point. So again it satisfies the criteria as we have seen earlier. Well, now let us look into the another example where we have a concentrated moment. Now, we will have to draw the shear force and the bending moment diagram for this particular beam, where we have a concentrated moment which is at a distance of A from the left end A, and this is B, and from this point 2 up to the point B it is B. The span of the beam or the length of the beam is equals to L. And as we have seen earlier, again this is supported on a hinge and this is supported on a roller, and as usual we will have reactive force here which is Ra, and a horizontal force which is Ha, and a vertical reactive force which is Rb. Now, here again summation of horizontal force will give us 0, which says that Ha is equals to 0. Now, summation of vertical force is 0 will give that Ra plus Rb is equals to 0. Now, here there are no vertical load, hence Ra plus Rb is equals to 0. Now, if we take the moment of all the forces with respect to A, and if we say that moment with respect to A is equals to 0, then we have Rb into L, which is in an anticlockwise form. Also, we have the concentrated moment which is acting in an anticlockwise manner. So, this plus m0, this is equals to 0. So, the value of the reactive force Rb, this is equals to minus m0 by L. Now, since Ra plus Rb equals to 0, so the value of the reactive force Ra is equals to minus Rb, and this is equals to m0 by L plus m0 by L. So, Ra we have got as m0 by L, and Rb which we have got as negative. So, it is in this particular direction which is m0 by L, minus m0 by L. Now, here we have two segments, one is from here to here one segment, and from this point to this point another segment. And if we take the free body diagram in these two segments, keeping in mind that Ra is equals to m0 by L and Rb is equals to minus m0 by L, let us see then what happens to the shear force and the bending moment diagram. Now, let us draw the free body diagram of those two segments, and you will get the bending moment and shear force as this. So, if I take a free body of this particular diagram at this segment, on the left side we have these as the reactive force. These are the forces at the cut segment, which is V and M, and this we have seen as m0 by L. So, summation of vertical forces will give V as equals to minus m0 by L. So, the value of the shear force at any point between the segment from here to here is not a function of x, it is a constant. So, everywhere we will have, wherever we take the section, we will have the value of shear force as m0 by L. Now, if we take a free body at this particular segment, then the free body becomes like this, that we have the reactive force which is m0 by L, we have the concentrated moment in an anticlockwise direction, we have the shear and the bending moment. Now, if we take the moment of all the forces with respect to this particular section, then we have bending moment m, which is anticlockwise, then we have m0 again which is anticlockwise, and we have m0 by L, and this distance is x. So, minus m0 by L into x, this is equals to 0. So, m is equals to m0 by L into x minus m0. Now, when x is equals to a, the value of bending moment is equals to m0 by L into A. Well, this is about the bending moment, and about the shear force what happens, this is V. So, V again is equals to minus m0 by L, and this moment does not have any effect on the vertical force, and hence the shear force is constant from here to here, which is equals to minus m0 by L. So, over the entire length of the beam, the value of the shear force is equals to minus m0 by L. Now, looking into the bending moment over here for this segment, m is equals to m0 by L into x from here to here. So, up to this particular point x is varying linearly. When x is equals to 0, the bending moment is 0. When x is equals to a, the bending moment is m0 times a by L. So, this is the value of the bending moment over here. Now, if we take the cut here and draw the free body diagram as this, and we compute the value of the bending moment, then we get the expression for the bending moment as this. Now, if we compute the value of the bending moment at a distance of a, we have m0 to a by L minus m0. So, if we take m0 common, then we have a by L minus 1. So, a minus L by L, a minus L is nothing but minus b. So, this is equals to minus m0 b by L. So, here you see on the left hand side we had a bending moment of m0 a by L. Now, the beam where we have the concentrated moment, on the left hand side we had a value of positive m0 a by L, and immediately next to that point of the concentrated bending moment we have the bending moment which is equals to negative m0 b by L. So, there is a sudden jump in the bending moment from the left to the right where we have a concentrated moment. So, this is what is reflected in this particular diagram. At this point here we have m0 by L and here we have m0 b by L, and again at x is equals to L, if we substitute here you get m0 minus m0 as 0. So, this is 0. Now, as I have told you earlier that at this particular segment, though we have drawn this as a straight line, now if I enlarge this part, basically since we have the moment at this particular point as a concentrated moment, we are computing on the left hand side of this particular concentrated moment, we are computing the moment value on the right hand side of the concentrated moment. On the left hand side we have got a positive m0 a by L, on the right hand side we have got negative m0 b by L, and basically the variation is something like this. So, here it is going from 0 to this value, then it is varying like this, and 0 to from this to 0 value. Now, this particular distance being very small, we approximate that as a straight line instead of that inclined line, and this is what is reflected in this particular diagram. So, this is the shear force diagram and this is the bending moment diagram with the magnitude of the moment and the shear values written over here. So, these are the bending moment and shear force diagram for this kind of beam where the beam is subjected to a concentrated moment. Well, let us look into another kind of a beam. As you can recognize this, that this particular beam is supported at this edge, let us call this as edge A, and this is end B. End B is unsupported or it is free, and we have defined this kind of beam, a beam which is supported at one end and free at the other, as a cantilever beam, and this particular cantilever beam is subjected to uniformly distributed load. Now, we will have to draw the shear force and the bending moment diagram for this particular beam. Now, to draw the shear force and the bending moment diagram, as we have seen, let us draw the reactive the free body diagram of the whole beam, and thereby let us compute first the reactive forces, so that we can. Now, the reactive forces will be, as you know, the vertical reactive force which is Ra, the horizontal force which is Ha, and a bending moment which is Ma. Now, summation of the vertical forces is 0, gives us that Ra minus Q times L is equals to 0. So, the reactive force Ra is equals to Q into L. Now, summation of horizontal force equals to 0 will give us Ha equals to 0, because there are no other horizontal forces. Now, if we take the moment of all the forces with respect to this point A, we have Ma, which is acting in an anticlockwise direction, and Q is the load, Q times L is the total load, and the moment of this load is equal with respect to support A is Q times L by 2, which is again in the clockwise direction. So, minus Q times L into L by 2, this is equals to 0. So, moment at A is equals to Q L square by 2. So, we have the reactive force R A as equals to Q times L and the moment as equals to Q L square by 2. So, these are the values of the reactive forces. Now, let us take the free body diagram of this segment of the beam, so that we can find out the values of the shear force and the bending moment at that particular segment. Now, if we, this is side A, this is side B, and we take a section over here which is at a distance of x, and this is R A and moment A. R A, as we have seen, as equals to Q times L, and moment as A equals to Q L square by 2. Now, if we take the free body diagram of this particular part, we have this as R A, we have M A, we have the uniformly distributed load which is Q, here we have load V, here we have load M, and this is at a distance of x. Now, as we can see over here that the vertical force V is equals to V plus R A minus Q x equals to 0. This is Q x minus R A, as we have seen as Q L. So, Q x minus Q L. Now, when x is equals to 0, V is equals to minus Q L, and when x becomes L, then V becomes 0. So, it linearly varies between Q L to 0, and this is the shear force diagram of this particular section. Now, if we compute, if we take the moment of all the forces with respect to this, we have moment which is in an anticlockwise direction, M A also in the anticlockwise direction, the load Q is also in the anticlockwise direction, which is Q x square by 2, and R A in a clockwise direction, which is R A times x, this equals to 0. So, this gives us a value of bending moment which is equals to R A into x minus Q x square by 2 minus M A, which is equals to Q L square by 2. Now, at x equals to 0, we find that the bending moment value is equals to minus Q L square by 2, and x equals to L, we find that this is Q L square by 2, Q L square by 2, this is 0. So, it varies again in a parabolic manner from minus Q L square by 2 to 0. So, this is the shear force diagram, and this is the bending moment diagram for this particular beam. Now, we have another example problem where you will have to draw the shear force and the bending moment diagram for this particular beam, and in the exactly in the same way for the hinge support exactly in the same way we write down the reactive force R A, the horizontal force H A, and the vertical force R V, and as you can recognize now, H A is equals to 0, we can compute R A and R B from the free body, and then we can take segments to find out the values of shear force and bending moment, and if we draw the shear force and bending moment diagram, they will look like this, that shear force here is 7.5 kilonewton negative. Now, at this particular point, now since we have the overhang beyond this, here it changes over to 12.5, and from 12.5 to reactive values here, it changes down to negative 10 and finally 0 over here. So, this is the shear force diagram for this particular beam, and if we compute the bending moment, you will find that the bending moment will vary again in a parabolic manner. The magnitude here is 2.5 kilonewton meter, at this point it is 5 kilonewton meter, and at this point again it is 0. So, this is the support point where we are getting the bending moment as maximum, as I had discussed in the beginning, that you can have maximum bending moment where shear force is 0, or where shear changes sign from negative to the positive or positive to the negative, and where there could be a reactive force at that particular point also you can have a maximum bending moment, provided you have a support reaction at that particular point. Now, we have another problem which is quite interesting, and many times we do come across in practical examples, where we have two beams A, B, C, D, this is one beam, and we have another beam DE. They are coupled together or joined together by an articulation. We call this as a hinge, and this particular hinge has a particular characteristics that it cannot resist any moment. Moment is equals to 0, but it can resist the shear force. So, what we need to do is that we need to find out the maximum shear force in this particular beam. Now, here again what you need to do is that you got to take the support reactions. Here we have vertical force, which is RB, and the horizontal one, which is HB. Here you will have RC, here you will have RE. Now, at this articulation point or at the internal hinge point, what you need to do is that if you draw the free body, you will have the force P over here, RB here, RC over here, and you have RD here. On the other segment, what you will have is RD will be downwards, because these two should be in a balanced form, and this will be RE. Now, if we evaluate the reactive forces, and exactly in the same way, if we compute the shear force and the bending moment, we can get the corresponding diagrams, which we have termed as shear force and bending moment diagram. So, you do this particular problem, we will be discussing this particular problem in the next lesson. Now, to summarize then, that in this particular lesson what we have done is we have recapitulated the aspects which we have discussed in the previous lesson. We have introduced the concept for the development of shear force and bending moment diagrams, and we have looked into some more characteristic features of shear force and bending moment diagram, and we have seen that how shear force and bending moment changes at a particular point depending on the concentrated load or the concentrated moment. Also, we have done examples to evaluate shear force and bending moment for different types of loading on different types of beams and plot of shear force and bending moment diagram. Well, this particular module then comes to an end that with these 4 lessons, and in this particular module consists of 4 lessons, and here we have introduced the concept of beam, the shear force and bending moment diagram. Also, we have known how to draw the shear force and the bending moment diagram through several examples, and these are the question set given for you. Now, what is the effect of articulation in an indeterminate beam? What is the effect of articulation in a determinate beam? And what is the necessity of drawing shear force and bending moment diagrams of beams? Now, the answers to these questions will be given in the next lesson. Thank you very much. Welcome to the first lesson of the 6th module, which is on stresses in beams part 1. In fact, in the last module we have discussed some aspects of the shear force and bending moment on beams, and in this particular module we are going to discuss that how to utilize those informations on shear force and bending moment in evaluating the stresses in the beam. In fact, today's lessons we will be discussing on the effect of the bending moment on the stresses in a beam. Hence, it is expected that once this particular lesson is completed, one should be able to understand the concept of bending stress in a beam. One should be in a position to derive the bending or the flexural equation. In fact, as we have seen in case of the torsion in a